Pre-statistics. Example 4. The wild Pacific Northwest salmon populations are listed in Table 48 for various years. Let P be the salmon population measured in millions at T years since 1950. Find a linear model that describes the relationship between T and P. Number 2. Find the p-intercept of the model. What does it mean in this situation? Number 3. Use the model to predict when the salmon will become extinct. So number 1, describe the data in terms of T and P in the table. So for 1960, T will be 10, 1965, T is 15, and we have the corresponding P values. We sketch the scattergram, and according to the scattergram, there appears to be a linear relationship between T and P. So we draw this line. Now from this line we see that p-intercept is 13 and we see that the t-intercept is 45. So the p-intercept being 0, 13 means, according to the model, there were 13 million salmon when t equals 0. So what we say is, according to the model, there were 13 million salmon in 1950. That's when t is 0. Number 3, the t-intercept is 45. Now what that means is when t is 45, p is 0. So to interpret this, we would say, according to the model, the salmon became extinct when t was 45, which is 1995. Now, this really didn't happen. Our model gave us a false estimate. Lesson objective number 3. When we use the blue portion of the model to make estimates, we are performing interpolation. When we use the red portions of the model, we are performing extrapolation. So if we look at the graph here, our domain for our x values range from 10 to 40. And when we pick x values within this domain, we are performing interpolation. When we pick x values outside the domain, less than 10 or greater than 40, we are performing extrapolation. And the further that we go beyond our domain, the more likely the model will have what's called a model breakdown. Let's look at a visual of this. Interpolation we can think of is inside the domain. Extrapolation is outside the domain. For a situation that can be modeled by a function whose independent variable is t, we perform interpolation when we use part of the model whose t-coordinates are between the t-coordinates of the two data points. In other words, as long as our independent variable that we pick is inside the domain, we are doing interpolation. We perform extrapolation when we use part of the model whose t-coordinates are not between the t-coordinates of any two data points, or we are outside the domain of the x's. So why do we need to talk about interpolation, extrapolation? Interpolation will likely provide us with a reasonable estimate using the model. When we extrapolate, the estimate may be incorrect. Let's look at an example. The average height of a 2-year-old male is 34 inches. The average height of a 5-year-old male is 43 inches. The average height of a 10-year-old male is 54 inches. And we see the relationship as the male gets older, his height increases. I put this data into the TI-83 calculator. Age is list 1, heights list 2. I perform the scatter plot. And then I found what's called the line of best fit, and we'll do this later. This is the line that models these 3 points. So it has an equation. The equation is y equals 2.5x plus 30, where y is the height, x is the year. Now let's use this model to predict the height of a 60-year-old male according to this model. 60 is our x. We multiply it by 2.5. We add 30, and we get 180 inches. Now what that means, according to the model, the average height of a 60-year-old male is 15 feet tall. Now of course this is nonsense, but this illustrates that when we extrapolate, we can end up with values that are nonsense. When we extrapolate, we are assuming that the pattern will stay the same, and it may not. And of course we all know once a male reaches 18 to 20 or 21 years of age, they're less likely to grow anymore. Lesson objective number 4. When a model gives a prediction that does not make sense, or an estimate that is not a good approximation, we say that model breakdown has occurred. We saw that in the last example. Example number 5. In 2002, there were 3 million wild Pacific Northwest salmon. Let P be the wild Pacific Northwest salmon population measured in millions, T years since 1950. Use the data for 2002 and the data in Table 50 to sketch a model where the population of salmon levels off at 10 million. Number 2. Use the data for 2002 and the data in Table 50 to sketch a model where the salmon become extinct. So this example here is illustrating we're going to come up with 2 different cases where we model this data. We add the additional data point, but we will end up with 2 different scenarios at the end. One will have the population leveling off, and the other will have the population becoming extinct. Now the first thing we have to do is add our new data point. We're going to use the order pair 52-3 because 2002 is 52 years more than 1950. For the y coordinate, we're going to use 3 because our units are in million. So when we plot this original data with the new data point, this is what the scatter plot looks like. And in this example, we wanted the population to level out at 10 million. So here's an example where the population is decreasing, and then it starts to increase, and then it increases till it levels off at 10 million. Number 2, we have the same data here with the new point, but this time the problem wants us to illustrate where the population would become extinct, and that would be approaching 0. So here we have 2 different cases for the same data. Whenever we extrapolate, we don't know once we go beyond domain what the pattern will be. Will it increase again? Will it level off? Will it decrease? We don't know. Thanks for watching.